Hello everybody and welcome back to another one. Today we are doing late code. No, just kidding. Today we are working on our data structures. The first one which we are going to need, and that is a linked list. So let's get right to it. Right, so linked lists. So how should we do this? I guess I'll just do list.sig. And we can get started on this. And the reason we are creating our own lists instead of using the ones that come with the standard library of Zig. So we do have singly and doubly linked lists in the standard Zig library. And we are not using them because of this node structure here. So basically the Zig lists return this node struct that basically has this next pointer and data for the singly linked list, and for the doubly linked lists it has the prev, next, and data fields. But I want these fields to be put into our data T. So what I want is an intrusive linked list, and that also allows us to have better control on the positioning of these fields instead of having them pretty much at the top of our structure here, like this node, putting them somewhere where they will not affect things like cache performance is actually pretty good, especially if we're not iterating this list all the time, which would be our case. So if we are using linked lists, random access is not really what it's suitable for. So we will avoid iterating it as much as possible. So we do want these fields here to be out of the top part of the struct, so that we can actually have, or we can actually control cache coherency if we want to do that. Right, so here I'm just taking a look at what sort of functions we have on the Zig library, and I think we are just going to implement the same ones. So should I just copy these over? I should do that, I guess. There we go. So let me just do this. And for now, let's just comment these out. So let's get started. So first, I'm just going to bring stud. I think we are going to need that. Then I'm going to create. So here we are going to take a generic T. So we are going to create a generic type. So I guess public function, call this singly linked list, and this one here would take a comp time T of type any type. Then we'll have a comp time. So this one is a single linked list. So next field, which would be stud meta and field enum of that type T, and we are going to return a generic type. Right. So here, let's start by doing this and a struct. Yeah, do that. And I guess inside our struct, we are going to need these. So let me just do this quickly. There we go. There we go. So first we need to define self. And self would just be at this. Then we are going to also need to define our data type, which in this case would just be our T. We're just going to give it a different name. Actually, yeah, I'm not going to give it a different name. And we want to get the name of this field here. So field enum basically returns an enumeration with, maybe I should show this. field enum. There we go. So if we look at the example we have here, we call field enum on this struct here that has a field A, and we get back an enumeration that has a field A. Same goes for this struct here, has ABC, and we get ABC here. So it works on structs and also on unions, so that's pretty cool. And we take this and we use it alongside field info. And this field info function here takes a type T, takes a field enum, and it returns a struct or a type info struct, basically. And what we can do is we can do something like this. This is a very good example. So we have an enum E1, or maybe I should look at the struct example. That's what we want to look at. So we have the struct S1, we have a field A. We do field info of S1 with the field enum, which we access with .a. And this one returns us SF, and we make sure that SF.type is U8, and we can do SF.name is A. So we want basically to use this, or to get SF.name, so that again we can use @field, which basically takes some generic T and some string, which is the name of a field, and lets us access that field from that generic type. And all of this is, of course, done at compile time. Otherwise, we are not going to be using it. Right, so let's go back to our code. Right, so here we want, what do I call this? Let's just call it next. And this next here will be stud meta.fieldInfo. Field info that takes a T and takes next field. Oops. Right. And actually we just want the name of that. So that basically gives us a const U8. Cool. Very cool. Just going to do this here, just going to replace list by self, and we should be good to go. This one is fine. This signature is fine. This signature is actually should return a pointer to T. That's nullable. So this one here should take a const pointer to, or rather a not const pointer to T, since we are going to modify its next field. And here we also want to, yeah, sure. This takes a pointer to T, since we are going to point T to basically jump one item of our list. Okay, so let's do this in order of priority. So I guess I first need to implement prepend, then probably length, then pop first, and remove is last on my list of priorities. I also would like to define a head, which here would be a nullable pointer of T, I guess. Yeah, we don't have any constraints on that. Cool. So let's get to this. So we want to prepend something to our list. So we basically check, do we have a head? So if we have a head that we capture as H, for example, if we have a head, we get our new node. So we are going to make full use of our new node here next. So our next field, or rather the next field of our new node, will point to head, to self.head, obviously. And then in either case, I think, we set self.head to be our new node. Obviously here is self.head. Unused capture, of course. Yep, right. So the next field is a t. It's a pointer to t. It's not a pointer to const t, to nullable t. So this one here needs to be h. There we go. So that's that for the append. So now let's do the length. This one should be fairly easy. So while self.head, rather, let's create a var cursor is self.head, and we are going to do right. So let's first do a check. So if self.head as let's just capture that as h, and all of this is going to go in there. Else here we are just going to return 0. There we go. So here we want this to be this, and while cursor actually, now that I think about it, the next field should be a nullable. So this one here would still be self.head, I think. Right, and we can get rid of this capture here. So same goes for here, but can we, if this is null, let's do something like this. Let's just return 0 over here and do something like this. Right. And here we just capture our cursor as C. H is undeclared, of course, so this one needs to be that one. And here we are going to defer cursor is equal to cursor dot, or rather at field cursor next. There we go. So now we get C. Actually, we don't really need this. We just need to var length is a u size. So this one is a u size, and we do length plus equals 1, and return length. There we go. So what do we shadow? Oh, right. Let's just write it out. Length. Length. Oops. There we go. Cool. So with these, we could probably write our very first test. So what should we call this? Append and length. So var, let's create a list, is a singly linked list of some type. So we need some type. So const this type is a struct that has, obviously that needs, so here we are just going to set a next field, and we are going to give it a field of nullable pointer to test type. Right, and this one can be set to null by default, and here we are going to have some value, which is a u32. Okay, So here we are doing, test type, and this one is .next. Right, so this one here returns us a list type. So can we probably rename this to test type list? And this can be a const. And here we can go list is our test. Should we do something like this? Nah, that's actually fine. So test type list. And we just create a new one. Right. So actually, before we do this, can we just do init let's give some more descriptive name to this. List should init with head null. Actually, let me just do something like this correctly. Should init. Right, naming is the hardest problem of computer science. Again, demonstrate live. Right, so here let's just do a check that our list. So set this thing dot expect. Do we have expect null? We don't. So we should do something like this. Yeah, that's fine. So list.head is null, is what we want. Is there something else we want to expect? Oh yes, we also want to expect that set.testing expect that list.length is equal to 0. That's very important. Use of undeclared. Right. I'm actually dumb as a brick. So let's do this, add this, and this one should be self. And that should make it happy. Right. So can I do this and probably just go back to so list append should increase length so list.append or prepend, sorry. So something like this, and we need to prepend something. So var node or node 1 is test type with value being 1 to 3. Yeah, okay. So this one just take node 1. Variable is never mutated. Actually, this one would take a pointer to that. That solves the problem. And here I'm just going to do node 2, which would take a value of 3 to 1. And just going to append that to, and here we should expect this to be that. Head should be node 1 and head dot next. So if we do field next something, yeah, this is getting weird. So we take the field next from head, and that should be equal to node 2. If everything goes well. So let's cd kernel source and sig test list.sig. Okay, missing structure field head. Of course, so this one just initializes to null. Expect type bool found whatever that is. So 11. Right. So we should probably do, or rather, let's do it the way they expect us to do this. Okay, so did I miss something? Expected bool found. Oh, right, sorry, I'm not reading the correct error. So 47. Using yep. So this one here should be tried. Same for these ones here. Should be tried. There we go. Right, let me just clear this out so I don't get lost. And of course here we should be at 66, rather 24, and we do the same thing here. We just discard the capture. Cool. So 25 type nullable list does not support field access. Right, so I guess here we do need to get a capture. Right, okay. And 66. So we do need to get that from that. Cool, so we do have an error. Let me just bring this back up here. So try to expect that list.head is equal to node 1, and that failed for some reason. Oh, of course. These are inverted. We are prepending this. So these two should be inverted. Cool. So we expect that head.next. Am I doing this wrong? I am. Am I not? Right. And this one should be that one. There we go. All tests passed. Cool. Right. So now let's bring this one up. So we want to remove the first element. So if we have a head, so self.head as an h, we basically set our head head is set to whatever that h.next. So whatever the field h and next is, and we need to save it somewhere, I guess. Yeah, we need to save it somewhere. So yeah, var popped item is self.head. Yeah, okay. And here we just return popped item. Right. So never mutated, of course. So this one can be a const. So let's think this through. We have self.head, we capture that. We set our self.head to the next item, which can be null, which basically empties our list. And in any case, we return the reference or the pointer to the item that we've popped off the top of the list. Cool. So I'm just going to think this through as we do this, but pop first should decrease length. Right, so here I'm just going to keep the same test and just going to make sure that we have a length of 2. We are going to, no, actually, let's dot pop first. And we need to get that somewhere. So const popped node 1. Right, so here we should expect this to be 1, and we should also try set testing expect equal. Actually, let me just get to. So now we want popped node 1 to be equal to the ref to node 2, and we want this to be have length of 1, and then we want to const popped node 2 to be pop first again, and then here we do try set testing expect equal, and we want popped node 2 to be node 1. Now that we have learned from our mistakes, and if I do go here and just put this down, and we can just set this to 0. Right, that looks like an okay test to do. So where do we mess up? Nowhere. Obviously. First try. Cool, so we have that done. Now here the remove, I'm actually unsure of what they mean by remove, since we cannot remove our current node without doing a O of n iteration over our list, since we need the previous element to remove our node here. So I'm just going to check if that's what they mean by that here. So removes a node of the list. It's actually pretty non-descriptive, but okay. Right, so they do walk. They do walk the list. Huh. Not really sure about this. I don't want to. I don't want to implement expensive operations in my library here. Prepend is pretty easy. Length is expensive, but I guess we do expect it. So okay. And pop is fairly easy too. So you know what? Let's do it. Let's do it. It's okay. Right. So let's do while. Well, I guess we need a cursor again. So cursor is self.head, and while cursor capture that as C, if field C next is equal to our node, then we to do basically shunt the priv and our next. But there's a case we are missing, because here we are checking directly the next nodes, whereas we are skipping the cursor itself. So let's do a check with just if self.head is equal to node. If that's the case, we set self.head to null, and we return. Yep, okay. And here we take the cursor, we get that, I guess this, no, we are going to mutate it. So defer cursor is field C next. There we go. Actually, can't we just do const cursor next is this, and here we can defer cursor is equal to cursor next, and here we can avoid doing this kind of thing. We can just replace this by cursor next. So if cursor next is our node, then we should do c dot. So in which way? Oh, so it's fairly easy actually. So c dot next is our node dot next. So field node next. There we go. That's fairly easy. Barely an inconvenience. Right. So while cursor, we capture that as C, and then we move this by 1. Right. So actually, okay, that's fine. The only issue I have here is we are comparing node which is not. So I have a doubt about comparing a nullable pointer to some t with just a pointer to that t. Does this compile, or is this an okay thing to do? Does the pointer naturally coerce to a nullable pointer is the question here. But I think we'll know fairly quickly if we just write a test for that. So remove should remove the first. I'm tempted to just write remove should work. Remove move in head results in empty empty list, I guess. Right, let me just go ahead and steal this. Right, let me just steal all of this, put that here. And so we have 2 items in our list, and we want to do this check here. And I also would like to do a check, this check here, over here. Right, so here I'm going to do list.remove, and I'm going to remove a node 2. Right, so hold on. Remove node 1. So for now, we are just going to. So this one should be equal to null, and this one should be. Oops. Right, so this one should be 0. Right, so removing head results in empty list, and then we should do. Whoopsie. There we go. Removing node should decrease length. I guess that's what we are testing for. Right, so here we do this. This value here goes to 321. we didn't check any of the values because we know that if we have the correct pointer, the value should still be there. Right. So this one here, this one there, and this one there. So we are trying to remove the second node, which is our new head after this prepend operation. So our new head here should be node 1. And this here should become 1. And then if we go ahead and try to do a remove on... actually, let's do another remove on node 2. Yeah, that's actually pretty interesting. Right, we should have pretty much the same things happen again if everything goes well. And then we are going to remove node 1. And this should become null, I think. And this should be 0. Right. Just thinking. So we have one other test case we didn't cover, which is if we... so let's do this again. Let's prepend with node 1. And... no, actually we are going to need a node 3, I think. Right, so let's go here, do something like this, and do 4, 5, 6. And so here we want this to be node 3. We are going to remove node 1, which is not our head, and we expect this head to not change. So this should be still node 3. This should still be node or length 1. Let's see where we messed up. So expected null found. Okay, that's kind of weird. So 1, 5, 2. So we are expecting head to be node 1. What? Wait. Oh, okay. Right, so before we run this, I'm just going to go back to all my tests and flip these two here. Right, so now our messages will be a bit more readable. So expected this in removing node expected to have a list, but found null. Cool. So, and that's in 152. So this one here, after we do remove of node 2, oh, right, this is so bad, so bad, so bad. So we need to, so if self.head as h, we do this next. Else self dot no, else it's already null, so there's no next. There's no else. There we go. So we are done with this.